100 trees just voted their way past one tree's mistakes. But strip away the votes, and every tree still cuts with straight line splits. So what happens when no straight line can separate your data at all? Picture two rings of dots, one inside the other. Any straight cut fails completely. That's exactly the wall support vector machines were built to break through. This is episode 10. Support Vector Machine Explained, Margins and Kernels. By the end, you'll watch a straight line fail at 50%, then fix it with one word. Every model we've built so far draws boundaries out of straight lines and cuts. Logistic regression, one line. A tree splits, straight cuts one feature at a time. Stack enough splits and you can approximate a curve, but it still boxes underneath. Some data doesn't care how many boxes you stack. It's just not separable that way. SVM throws out the box-cutting approach and asks a completely different question. Here's the SVM idea. Don't just draw a line between classes, draw the best one. Imagine the widest possible street you can fit between the two groups of points. The line down the middle of that street becomes your decision boundary. A wider street means more confidence and better generalization to new points. That's the maximum margin the entire optimization SVM is solving. Which points decide where that street actually sits? Not all of them. Only the points closest to the boundary, right on the edge of the street, matter. Those are called support vectors. Literally, they support the margin. Move a support vector and the boundary shifts. Move any other point, nothing changes. Most of your training data could vanish and the model wouldn't even notice. Real data is messy. A perfectly clean street rarely exists. SVM allows a soft margin. Some points can sit inside the street or even cross it. The C parameter controls exactly how much of that gets tolerated. High C. Punish every violation, narrow street, risk of overfitting. Low C. Tolerate more mistakes, wider street, usually better generalization. Now picture this. One class forms a ring around the other class entirely. No street, no matter how wide, can separate a ring from its own center. Any straight boundary here is basically guessing, a coin flip, nothing more. This is exactly where every linear method we've covered simply gives up. SVM has one more trick left, and it's the one that made it famous. The kernel trick. Lift the data into a higher dimension where it does separate. Add a third dimension like distance from the center, and the ring lifts into a cone. Slice that shape with a flat cut, and the two classes fall apart cleanly. Here's the wild part. SVM never actually computes that higher dimension. It computes the result of that lift using a kernel function, pure mathematical shortcut. The most common kernel by far is RBF radial basis function. It measures similarity as influence decays outward, perfect for ring-shaped patterns. Gamma controls how far that influence reaches. High gamma, tight, wiggly boundaries. Low gamma, smooth, broad boundaries instead. Scikit-learn defaults to RBF for good reason. It handles curves right out of the box. In Scikit-learn, this is SVC support vector classifier. Import it. Set kernel to linear or RBF. Call.fit. One keyword, kernel, is the only difference between a straight line and a curve. And _support_ tells you exactly how many points became support vectors. Same three-line pattern as every model this series, just a smarter boundary underneath. 200 points, two concentric rings, inner ring one class, outer ring the other. SVC with a linear kernel, 50% accuracy. Apure coin flip. It needed 132 of 140 training points as support vectors and still failed. Same exact data, kernel set to RBF 100% accuracy using just 30 support vectors. One keyword changed. The result went from a coin flip to perfect. SVM shines on small to medium datasets where a real margin exists to find. The kernel trick makes it genuinely powerful on nonlinear boundaries. It's less forgiving at massive scale. Training time grows fast with more data. And it needs feature scaling. Distances matter, so put every feature on the same scale. For small, tricky, nonlinear problems, it's still one of the sharpest tools available. Let's lock in what we covered. Maximum margin, the widest possible street between the two classes. Support vectors, only the closest points actually decide the boundary. Soft margin and see how much rule breaking the model tolerates. The kernel trick, separating data by lifting it without ever computing the lift. RBF kernel, the default that handles curved boundaries right out of the box. If kernels just clicked for you, subscribe. KNN is next, and it's refreshingly simple. Quick look at where we are in the series. We've covered decision trees, random forest, and now the margin-based world of SVM. Episode 11 is K-nearest neighbors, a model with no training phase at all. It just looks at whichever points are closest and votes. Episode 11, K-nearest neighbors explained. No margins, no kernels, just distance to your nearest neighbors. The simplest model in the series so far. Subscribe to catch it. Your challenge task for this episode. Generate 2 concentric rings of data with Scikit-learn's make_circles. Task 1. Fit SVC with kernel equals linear and check test accuracy. Task 2. Fit SVC with kernel equals RBF on the same data. Compare the gap. Bonus. Print n_support_ for both. How many points did each one actually need? Try it yourself first. The full solution is in the repo. Post your linear versus RBF accuracy gap in the comments. One keyword, kernel, took a coin flip to a perfect score. That's the maximum margin, lifted into exactly the right dimension. Episode 11, K-nearest neighbors explained, drops next. Subscribe. Comment with your own linear versus RBF accuracy gap. I'm Majas. This is CodeToAGI. Let's build.